Good morning and welcome to the Chrome 6 Demonstration Study Project Advisory Committee meeting. It is September 9th, 2010, and we're in the City Hall Council Chambers at the City of Glendale. I'm Pat Hayes, Principal Civil Engineer in the Water Engineering section. I'm filling in for Peter Kavunas, who will be hopefully joining us a little later this morning. He was detained this morning and couldn't be here for the initial remarks. This is the second meeting of the committee. The last one was about 4 years ago, and in the meantime, a number of things have progressed. It's my pleasure to now introduce the members of the committee. I'll have them each self-introduce, starting on my far right.
Okay. Good morning. I'm Pankaj Parekh. I'm the Director for Water Quality with the City of Los Angeles and a member of this PAC.
My name is San Liang. I'm with the Metropolitan Water District of Southern California. I'm with the Water Quality. I'm a Water Purification Unit Manager.
I'm Bruce Mackler with the U.S. Environmental Protection Agency in the San Francisco office. I'm in the water program, the regional toxicologist, and also oversee the drinking water R&D program.
And I'm Rick Sakaji. I'm with East Bay Municipal Utility District. I'm their manager of planning and analysis for water quality. When I joined this PAC, I was actually with the California Department of Public Health in their drinking water program.
And Nicole Blute, please introduce
And I'm
yourself.
Nicole Blute. I'm with Malcolm Perney, and I'm the project manager for Malcolm Perney on this project.
Thank you. And online, we hope to have one of our panelists, Heather Collins. Heather, are you there?
Yes, I'm here. Heather Collins. I'm currently with the California Department of Public Health, and I'm a regional engineer in Southern California for the drinking water program. Sorry I couldn't be there with you today in person.
We understand you have a broken wrist, and we wish you speedy recovery for that, Heather.
I appreciate that. Thank you.
Is there anyone else online who has called in that would like to introduce themselves at this time? Hearing none, I'll proceed. We might have Eugene Lung calling in as well from the California Department of Public Health, so we'll expect to hear from him a little bit later. The meeting today is to brief the committee on the operational activities of the two Chromium 6 demonstration study projects and their facilities, and what has occurred to date at those facilities, and also, more importantly, to look at options for the operation of the facilities for the next few months. We're fortunate to have all of these PAC members represented here, and Heather online. They provide extremely valuable input to the operation of these breakthrough facilities. We have many people in the audience today. We had about 40 people RSVP. We don't have quite that crowd, and I think we are speculating that a number of them, when they found out that this is being televised by GTV6 and online, may be taking that option rather than traveling today. So we welcome the audience and hopefully your questions as well when you feel it's an appropriate time. Nicole Blute from Malcolm Perney will provide the technical information, supplemented by comments from Camp Dresser and McKee, who are the operators of the facilities. The day's activities are outlined in the meeting agenda, which were passed out to all the parties that are in physical attendance. And just to confirm, Heather, you have a copy of the meeting agenda and the slides?
That is correct. Thank you.
Thanks. The morning session will be from now until noon on the technical part of the program, at which time we'll break for lunch over in the GWP facilities for about an hour or so, and then we'll take a field trip to the two facilities. Maps will be provided so that you can find your way out to the two facilities. One objective of this meeting is for feedback from the PAC on the technical information presented, on where we have been and where we should be going relative to the research. I'm certain you will gain a lot from the today's activities. And at this time, I'd like to turn it over to Nicole Blute for the presentation.
Thank you, Pat. Presentation today will bring us up to speed on the demonstration studies that are ongoing and have been so since April. So we'll start with the outline for the presentation. I'll start with an introduction just to kind of bring everybody up to speed with where these technologies were selected from, and some of the specifics about the technologies and how they're supposed to work in terms of removing Chrome-6. The first one that we are testing is called Weak Base Anion Exchange. You'll see WBA as an acronym throughout the presentation. And I'll first give a quick technology review, just how this works and what we're expecting to see in terms of treated water out of the system. Follow that up with some of the startup and operational issues. This is really the lessons learned part of the presentation, where it's one of the reasons that you have a demonstration facility before you go to a full-scale facility, so that you can really iron out all of the issues associated with it and move forward very expeditiously with a full-scale treatment. And then I'll talk about the chrome removal to date, so how well are the technologies removing chrome. Discuss some of the residuals issues, like for weak base anion exchange, the resin disposal issues, which we have an additional grant from the Association of California Water Agencies, ACWA, to look at this in more depth, because the residuals from the process can really be cost drivers as well as more difficult to handle. And then finally, we'll discuss the remaining study approach for the remaining 6 months of operation, and we'll get some discussion going between the PAC members. And then we have basically the same setup for the reduction, coagulation, filtration, the RCF process, and follow that up with discussion as well. So jumping right in, the introduction is, I just wanted to give a feel for the many different funding sources that are helping to support this work. The US EPA is one of the primary funding sources, and California DPH through the Proposition 50 funding. The Association of California Water Agencies sponsored part of the residual study, including looking at disposal options and costs. And then there has been some additional support from the Glendale Respondents Group, particularly for the carbon dioxide system that I'll talk about as we go through the slides. Okay? So the weak base anion exchange technology is basically the idea of filtering out chromium. Chrome-6 is removed using this particular type of resin. So chrome is exchanged onto the surfaces of the resin beads. They're very small beads, less than a millimeter in diameter. And the chromium is then retained on the beads. And what we found in some bridge project studies prior to these demonstration studies is that the chromium is actually reduced on the resin. So it becomes chrome-3, and then it's stabilized on the resin, and the resin has a very high capacity, much more than for a regenerable anion exchange facility, which is more standard for chrome-6 removal. So one of the unique things about weak base anion exchange is that you do need to reduce the pH to 6.0, and that's being done in this particular case with carbon dioxide addition to the water. Another option would be to add acid. As I mentioned, the mechanism is the reduction of chrome-6 to chrome-3 and retention on the resin, so that the chrome-6 is not in the effluent water. The expected resin life, based on a target effluent goal of 5 ppb, micrograms per liter, out of the effluent of the second bed. So these facilities are operated in lead lag configuration, where the water goes through the first bed and then through the second bed in series. And that allows you to maximize how much chromium you absorb onto the resin in the first bed before you need to change that out. So given those assumptions that you're looking at a target goal of 5 ppb out of the effluent, the expected resin life is about 200 days. And I'll go into some of the issues that can be considered if you want to extend that or cut it back. I'll talk a little bit about that. And again, the facility was started up on April 1st. So now jumping right into some of the startup and operational issues. One of the very first issues that the PAC and the operator, CDM, had to deal with was formaldehyde leaching from the resin. The resin itself is a phenol formaldehyde polymer And it was not expected, but we did find that some formaldehyde leached off of these resins initially, particularly when the resin sits in the vessel and doesn't have water flowing, so it equilibrates into the water. We also did see bacterial contamination because the vessels, there were some startup issues with the facility, and the vessels sat stagnant for a little time, and so bacteria built up on the resin. So as a result, what had to be done was what's called the brine squeeze procedure that Siemens did, which was to remove the resin back out of the vessels and then perform this process, a pretty substantial process that could take a day or two at the Siemens facility, including first backwashing, then a caustic wash, sodium hydroxide, followed by a rinse, and then an acid wash, another rinse, another caustic wash, another acid wash, and then finally rinsing to obtain the optimal pH and neutral pH for the resin. And then we did find that all the steps did have to be at elevated temperatures as well. So this was a process that actually required some playing with, and this hadn't been done before. So we learned a lot during that process, and in order to make sure the resin was ready to come back to the facility and not leach formaldehyde and not have the bacterial contamination issues that were first seen before the plant went online, there was a significant amount of testing that was done of formaldehyde, of total coliforms, E. coli, and heterotrophic plate count, HPCs. And then the resin, while this testing was going on, it does take some time for the laboratories to conduct that testing, the resin was continually flushed, so we didn't wind up back in the same spot as we were initially with stagnant resin. Now, it was effective, the brine squeeze procedure, so the resin was redelivered to the vessels, and the resin was backwashed initially to remove fines and remove any residual formaldehyde that might still be there. We did find that we needed at least 3 Baker tanks that are 20,000 gallons each, so a significant amount of water storage. And that really was because the sewer discharge permit for the city of Glendale at this particular location necessitated having non-detect levels of formaldehyde in the water. So some treatment needed to be done because there were some minor levels initially. And also, there's a limit on the flow rate of what could go to the sewer at a given time. So then that was followed by a forward flush, repeat testing, and then the water was finally delivered to the Glendale Water Treatment Plant, where it blended with the other well water, and then at that point the water was served. In terms of bacterial contamination, some questions arose during this process. One of which was, how could this resin be disinfected if positive bacteriological samples were observed? And we don't know that we have a great answer for this at this point in time. So this remains one continuing issue. So once the brine squeeze did work very well, but now once you have the resin in place, if you have a bacterial problem, what can be done at that point other than taking the resin back out again? So the brine squeeze is one option. A couple other options that might be possible are caustic, as done for GAC at the Glendale Water Treatment Plant, and potentially some other non-oxidative processes. So this is something that still is a little bit of an unknown. Luckily, we haven't had to deal with it because there haven't been bacteriological growth problems on the resin at this point. pH monitoring was another startup and operational issue. Initially, there was a pH probe put in line at the weak-base anion exchange facility on the influent. So after the water had the carbon dioxide added to the water to depress the pH to 6, we wanted online monitoring to make sure it actually remained there at a pH of 6, because the resin is not as effective at removing chromium at a higher pH. The first probe failed, which was hypothesized to be because it was allowed to become dry in the pipeline. The replacement probe that was sent from the facility didn't work, and now this third probe is actually found to be very effective. CDM is doing preventative maintenance at a pretty aggressive time frame of calibrating once a week, just to make sure that they stay on top of this probe that works. One other thing that we noticed and expected to see was that concentration differences are observed from grab samples that you take from the water compared to inline samples. And that has to do with carbon dioxide off-gassing and the pH increase of 0.2 to 0.4 pH units during off-gassing when you actually take your sample. So having that online monitoring is really important for this process. Another issue that came up was sound complaints from neighbors of the weak base anion exchange facility. You can see on the right-hand side that there's a fence right here, and this is a residential neighborhood. There are houses right here. So a couple of the things that caused these sound complaints were initial tank filling of the carbon dioxide and the carrier feed pumps for the carbon dioxide system and the static mixer. So what was done to resolve this issue was a sound barrier was constructed around all four sides of the pumps, leaving open the top for heat dissipation. And that has worked. So now moving into chromium removal to date, this might be a good time to have the PAC ask any questions related to operational issues if we want to discuss that. Yes.
Nicole, thank you for the good overview there. A question I had was the pH probe being calibrated weekly. Is that something you expect is necessary as due process from now on, or is it just something particular that you're trying to address in terms of maintenance? And is it being determined further, or are you accepting that weekly maintenance is just due process?
I might defer that to Charles or Rich. In your discussions with the vendor of the pH probe, did they recommend that, or how did that come about?
Good morning. My name is Rich Boudet with CDM. What we've found is the probes, it tends to drift a little bit. So if it drifts, we were using more CO2. Mm-hmm. So to try to keep that a steady usage, I was calibrating weekly.
I guess, sorry, I should have clarified. Is that something you consider a regular feature of the probe, or do you want to look for other probes that may not shift as much?
I think it's probably wise to say that we would maybe look at other probes to make sure they don't drift.
Okay, fair enough. Thanks.
I can add a little bit. I'm Eric Lang. I work for AECOM, and I was a project manager for the design build. And I've run other systems like this, and typically pH probes are somewhat finicky, the nature of the beast, and they generally require a weekly calibration.
Okay, thanks.
Okay, I have a question on the same thing. You indicate the third probe is working, so what difference between third one and previous two? You just cannot say that, you know. You need
Good question. I don't know if anything was ever figured out as to why. The first one I'd heard that it didn't work because it had been left dry for a while some of these other brine squeeze issues were going on. That did take a fair amount of time to pull the resin out and treat it and come up with the procedures that needed to be done. The second probe just didn't work is what I heard. It never calibrated properly. So.
Okay. Follow up with that. I know your operational target for pH is 6.0. Then you indicate you have the based on the measurement about 0.2 to 0.4. So is that tolerable?
We do think that is tolerable. During our bridge study, we did find that a pH of about 6.4 might be okay. But that being said, we don't think that the system is actually operating at 6.4. We think it is at 6.0. It's just when you take a sample and expose it to the air, it very quickly off-gasses CO2 and you get a higher result. You can watch the pH probe go up.
I have another two questions. One is, I want to clarify what you say. You say this demonstration scale, the treat water, served to public?
It is, yes,
Really?
yes. It's a 425 GPM system.
Okay.
And the water blends with the transmission main at the south transmission unit.
Okay.
Goes up to the Glendale water treatment plant where it's treated further for VOCs.
Okay.
And then it actually goes through air stripping and then GAC, and then it's chlorinated and chloraminated. So it does blend with the other facilities.
It's a blend. Okay.
Yes.
And another one is, I know we discussed that before, is your treatment goal for Chrome 6 is a 5. How did you determine that?
That is somewhat arbitrary because the MCL for total chromium is 50. So the levels that we're looking at here are significantly below that. But as part of the research study, we wanted to be able to look at how low we could actually go in this process, since this is a research study and we don't know where the chromium 6 MCL will end up. So we looked at 5 as a target goal here. There's also another issue, which is the Glendale, the ability to discharge water to the LA River is limited to 8 parts per billion. And so that went into that calculation of what level we should be at to allow then process upset water at the Glendale water treatment plant to be diverted to the river.
But you also aware of the OEHA issue, the public health goal, is that right? The 0.06.
0.06.
So that's potentially MCL can be lower than 5.
And that is one of the questions. So we have been looking and using methods that can get to lower levels. So we will have that information available after the demonstration study. How low can these technologies actually go?
Thank you.
Sure.
Nicole, I had a question for you on the brine squeeze. These are NSF certified resins, correct?
They are.
So is the brine squeeze considered a part of the certification, or is that done prior to certification, or is it done after certification? And then does the certification of those materials actually hold through the brine squeeze process?
That was one of the reasons we were surprised by the formaldehyde issue, because the resin did pass the NSF certification, and this was not raised as an issue. So it was something that was discovered after the fact. And so we did make sure that all NSF certified chemicals were used in the brine squeeze process. But it is a good question about what the future of these resins is in terms of meeting that brine squeeze in order to be used.
Yeah, so I guess what I'm looking for is, do you know if the brine squeeze would be done or performed by the manufacturer as prior to their certification of the materials, or would it be done at the site, or is that something that has yet to be determined?
Right now it's being done at the site, or at the Siemens facility, but not by the manufacturer of the resin itself. Maybe Heidi might have more, she might be able to weigh in on this.
Hi, Heidi Munoz from Siemens Water Technologies. Actually, the brine procedure is done at our regeneration facility in Los Angeles, and it's done after we receive it from the manufacturer. But we are working closely with the manufacturing to develop future methods that will possibly eliminate the need for the brine squeeze. So it's definitely being taken into consideration for future O&M costs of this project. So we're working together.
So from the standpoint of using the certified resins, though, they would lose their certification when they came into your facility, or is your facility also NSF certified?
I'm not sure at this point, but we can definitely look into that and probably answer that question to you at a later time.
Okay, thank you.
You're welcome.
I'd like to extend on that and ask if NSF has been involved in this part of the study. It does bring up the question as whether the certification criteria are appropriate for this, and whether they need to change things now that you have information that they probably didn't have.
I don't believe they've been
involved.
involved.
Has NSF been involved?
I think so.
That would be a
That's not-
recommendation to bring that back, because if you would be seeing this as an issue when you're specifically looking at it, it was fair to say that others would as well if they used this approach for hexavalent chrome treatment, and it would be good to get this going, whatever it might take, ahead of either California or EPA doing a modification of our regulations.
We'll definitely bring that.
Okay.
But at least this resin is NSF certified, right?
It
For
is.
drinking water.
It is.
NSF certified, but still leaching formaldehyde.
Yeah.
that brings up the question is of whether the certification is appropriate.
And it hasn't been in service in drinking water treatment for very long. It was certified for this project.
Nicole, sorry, on that same point, NSF certification allows up to 10% of any, contaminant of 10% of the MCL. What were the numbers with the formaldehyde?
Well, it only has a notification level.
There's no
California.
MCL.
There isn't any,
There's
right?
not an MCL.
So Bruce's point is on target, that we need some, this may be an example to use for NSF, because we have approached NSF on similar issues for non-MCL contaminants and having some policy and stuff, and they're looking for examples in the drinking water industry to arm themselves up with developing something like that.
Great.
I think this will be very useful. Great point from Bruce.
And we did, as part of this process, it's worth mentioning at this point, do a very extensive analysis of everything you could think of to see what else might leach from the resin, including tentatively identified compounds, things that couldn't necessarily be picked out but did cause a blip in a mass spec or something like that. And we didn't see anything that was suspicious. So,
Thanks.
okay. Thank you. So we'll move on from the operational issues and get into the data. Now this is the total chromium data for the weak-base anion exchange facility. And what you're seeing here, get the pointer, is the chromium concentration on the y-axis from 0 to 50 parts per billion, the number of bed volumes on the x-axis, which is a way of normalizing the amount of water flowing through the resin versus the actual cubic feet of resin that are present in the vessels. And so I've shown here the influent concentrations have been about 35 to 45 parts per billion for this. This is one particular well, the GS3 well. And then we've underlain the pilot study results from a previous pilot that Glendale did and then overlain the actual results from this study. So in blue, we have the total chromium concentration on the lead bed, or the first bed that the water goes through. And then in red, we see the chromium concentration coming out of the lag bed after it goes through the lead and then through the lag. And what we're seeing is really great agreement with the pilot study results, indicating that that was a very good way of predicting bed life. And what we're seeing is that we expect to see bed life to about 95,000 bed volumes, which corresponds to about 200 days of service before we get 5 ppb breakthrough on the effluent, the lag bed. Okay, next slide. Now, one thing that we also tested was the 50% bed depths for the two vessels. So now we're looking at sort of a midpoint of the lead vessel and a midpoint of the lag vessel. And by comparison, the results are really all over the place. So if you look at this purple line, that's the lead bed 50%, and sometimes it gets higher than the influent concentration. And then we also see the lag bed 50% is in blue, and that one also is pretty spotty. So what we're seeing here is we think that there might be a problem with the way that we're using the sampling ports for two different purposes. We're using it to sample resin, so the screens have been removed. And so as a result, you wind up with a slug of resin in the sample line that is discharged when you take a sample of water. So normally when you're sampling water at a 50% bed depth, you have a screen, and so you don't collect resin. And so you essentially have a mini ion exchange column in there, as well as some resin, and that's been equilibrating in the sample port line. So we're getting really spotty results. So we don't think it's worthwhile to keep sampling these 50% bed ports. We think it's kind of a waste at this point. There's also the other issue here, which is that we are sampling resin once a month, and so there could be short circuiting right around those sample ports as well. So we're not seeing great results there. We're getting much better results, as seen on the previous slide, from the effluent from the lead bed and the effluent from the lag bed. So that might be a potential cost savings to reduce sampling at those points. Now, one of the tasks that we had in the Aqua study is to assess what the weak base anion exchange residual disposal options were. And so in this process, we developed a decision tree, noting that there are two main drivers for this decision tree. One is whether the waste becomes radioactive, because it just naturally accumulates uranium that happens to be in the water at very low levels that are below any MCLs for uranium. And then also, the weak-base anion exchange resin can become hazardous because of the accumulation of chromium over time. It accumulates so much chromium that it can become a hazardous waste. We also looked at disposal facilities and which facilities would accept different kinds of waste. And so when we went through the exercise of determining what criteria for waste we might have, we looked at different disposal facilities. We got cost estimates from them, quantities they would accept, and how to actually go about doing disposal. Okay? Here's the decision tree. It might be easier to look at your slide, your handout, to be able to see this in detail, but I'll just walk through it really quickly. First, the first question is to determine if it's really a solid or more of a liquid. So you do the paint filter liquids test here. And so if it is considered a solid, we go down into this tree. If it's not a solid, then you need to separate out the liquids and then start over again in the tree once you do have a solid. So now into this part of the tree is the waste, RCRA hazardous waste. This is what's considered a federal hazardous waste that essentially fails the toxicity characteristic leaching test, leaching procedure, the TCLEP test. And so if this is an RCRA hazardous waste, then you get into the next question of whether it contains radionuclides like uranium. If it does not, you can dispose of it in a hazardous waste landfill. If it does, the question becomes, well, does this waste contain greater than 0.05% source material like uranium and thorium? If it does not contain greater than 0.5% source material, then you can dispose of the waste in a hazardous waste landfill that's licensed to accept technically enhanced hazardous waste, like it's called TNORM, naturally occurring radioactive material. I lost our pointer. The other branch there is yes. If the waste is considered a source material with greater than 0.05%, it does need to be disposed of in a low-level radioactive waste landfill that's licensed to accept a mixed waste. Mixed waste being it's both hazardous and it's a radioactive waste. Thank you. Now, going back up here, if the waste is not a RCRA hazardous waste, which is the case for the weak-base anion exchange resin, the next question is it a waste that's a California regulated hazardous waste? Because California has another type of test called the waste extraction test, the WET test, to determine if it's a hazardous waste, besides the federal TCLEP test. And so that leads us into this next realm. If it's not considered a California regulated hazardous waste, then you also go through and you find out if it's radionuclide rich or not. If it is considered a California regulated hazardous waste, but not a RCRA hazardous waste, and this is the path that we're taking with these weak base resins, then the next question is, does it contain radionuclides? If not, you can dispose of it in a non-RCRA hazardous waste landfill. If it does, then the waste if it does contain greater than 0.05% of source material, then you can be put into this bin where you're disposing of the resin in a low-level radioactive waste landfill that accepts non-RCRA hazardous waste. Clear as mud. Okay, so we did this analysis, and that's basically where we wound up. We wound up looking at these two options, this one here and this one here. So Glendale really had two options here. They could either run the resin to saturation or to the point at which they got 5 ppb chromium out of the effluent bed, which would lead to a buildup of uranium so that it triggers, it becomes a source material, greater than 0.05% by weight uranium source material. Or they could operate it to avoid that limit and so really focus on the uranium level and be able to send the waste to a non-RCRA hazardous waste landfill. So those were the two options. I can actually move this now, can I? No? Okay. I won't try it. So these are the two options I mentioned. One is really to operate the resin to saturation, which Glendale won't be able to do because of the permit requirement, but other utilities might be able to do. So we wanted to give an apples-to-apples comparison for other utilities if they're weighing these options. If they're saying, can we run the lead vessel to saturation, or should we really try to limit the amount of uranium that is accumulated to prevent having to go to a low-level radioactive waste landfill? So you see the estimated resin operation time on that lead bed is pretty different, 414 versus 170 days. And so what it came down to, bottom line, is that the costs were less if you ran Chrome 6, if you ran based on going to Chrome 6 resin or saturation, because the resin is so expensive. If you really focused on the uranium accumulation in the vessel and changed it out much more frequently, the extra disposal costs associated with a low-level radioactive waste did not overcome the extra costs associated with the resin. And part of that has to do with because the resin is only available from one provider at this point in time. There's only one of these weak-based resins that's been NSF certified at this point. So the cost is the cost. There's not a lot of bargaining power there. So what Glendale decided to do was to keep operating the resin, knowing that it would eventually trigger the source material level. And why this was decided was to really gain more information for other utilities, because this approach actually is costing Glendale a little bit more. It's going to cost about $300,000 instead of $161,000, because we are looking at a target effluent level of 5 ppb rather than going to saturation on the first bed. Now, you don't have to read all of this, but this is just to kind of give a highlight of the mass balance that we performed of the uranium concentrations. The uranium in the raw water, we're seeing about 4 micrograms per liter. It's pretty low level. It's what's considered pretty low level. We're seeing less than one part per billion coming out of the lead vessel effluent. So we're really getting full removal of the uranium by these resins. So they're very effective at removing uranium from the water as well as chromium. So now if you calculate out how much we're talking about, we're getting about 9 grams of uranium per day on these resins. So now there's 2 scenarios. There's the first scenario, which was when what Glendale's doing, where chromium concentration reaches 5 micrograms per liter on the lag bed effluent. That leads to an operation number of days of 187. And about 3.8 pounds of uranium, because there's actually some special licensing that you need if you have more than 15 pounds generated in a year. So we had to go through and do these calculations. So that special licensing was not required. And what we wound up expecting the resin to get to is 0.054% under these conditions. So just slightly over the limit that will trigger low-level radioactive waste categorization. So now the other scenario which is a worst case of chromium reaching saturation in the lead bed, so what other utilities might choose to do if they had uranium concentration similar to Glendale, that would lead to about 8.4 pounds generated or accumulated on the bed. So still below the special licensing requirements. Okay. Now, we've also been doing uranium sampling of the resin. As I mentioned, we've been taking resin samples. By we, I mean CDM. We've been doing resin samples for uranium at 25% lead bed depths, 50%, and then most recently a composite sample of 3 different bed depths. And we're seeing so far we are still below, if you focus on the one on the bottom, we're still below on a composite basis, the 0.05 at this point in time, which is what we'd expect based on only being about halfway to the point at which we want to change out. Okay. So now the remaining study approach, before I open this back up for discussion, the plan is to continue running this resin until we reach 5 ppb in the effluent of the lag bed, which will trigger the change out. The idea being we will need to dispose of this spent resin at Energy Solutions in Utah, which is the one facility on the West Coast that's able to accept this low-level radioactive waste. We will then evaluate the steady state bed life in the lag bed by replacing the lead bed, or changing the lag bed into the lead again, and then seeing where we're at in terms of concentrations and how long the bed lasts. And then we'll finally develop costs, evaluating several MCLs and how that might impact California utilities in particular. We'll develop costs on the carbon dioxide usage rates, disposal costs, and that's again where the Aqua study ties in. And then develop the costs more formally for the formaldehyde treatment. Okay. And then if anybody has any questions.
Yeah, I do have some question. Just point of clarification. You say you have VOC go to your resin, right?
VOCs?
Yeah.
Yes.
So what kind of VOC and the concentration? And also, have you think the impact on your bacterial contamination?
We haven't seen continuing bacterial contamination on these resins. In terms of VOC concentrations, I don't know if that's actually monitored. Do you guys monitor monthly VOC removal from the facility, or is that just RCF process? That's only in the RCF.
Just monitor the raw water on a monthly basis.
Okay, so just the raw water. So we're not looking at how much VOCs are removed by the resin.
I'm not saying removing. I remember correctly, it's a resin operation.
Oh, that's the RCF process. So we'll get into talking about that, yeah.
Oh, okay. Okay. And in terms of the uranium, have you measured the radiation around the vessel?
We've been told that that's not a problem based on the isotopes of uranium, that they can't actually penetrate the vessel wall.
Well, sometimes somebody see is one thing, to verify it's another thing.
I don't know if anybody's taking a Geiger counter out there, no.
Good point. Okay. Thank you.
But that will be done during disposal.
Okay.
Sure.
Okay.
Nicole, a general question on the chromium concentrations, the influent ones. Have you planned or did you do some challenge tests on this technology in terms of what the tolerance level would be for higher chromium levels in influent?
We did. We have tested it up to 100 parts per billion in pilot testing.
Okay.
And we wanted to use this as a standalone process because Glendale already had these vessels at the site, so it saved on capital costs, which is why it was selected for that particular well. But it does seem to behave well at 100 parts per billion as well. We haven't looked beyond that. But at that point, it might start to get much more cost prohibitive because you only have a certain capacity and the resins are expensive.
Okay. Perhaps this is a question for Glendale then, in terms of your projected concentrations, worst case scenario, what sort of chromium numbers might you expect from the monitoring you've done so far? Do you know?
Don might be able to answer that. There's a poster over there.
Got a poster. Good.
Are you asking at groundwater?
Yes.
In the groundwater?
In the groundwater that, theoretically would be what you'd like to run through these this final plant. And
The numbers that the EPA has projected showed an upward trend. We have seen some of that, not all of that, materialize at this point. EPA has reviewed their model and are standing by it. Perhaps there's a little more of a delay than they originally thought. I'm going off of memory, but I think the northern wells we're expecting to see concentrations of 170 parts, and those, of course, would hit the RCF facility. For the WBA, Leighton, refresh my memory, was it about 70 parts for the 50? So 50 in the south that would be going to the WBA.
Perfect. I'm glad you clarified that because I knew of the higher numbers, but your strategy seems to be quite adequate to split the waters and have the higher chromium go through the...
Just a couple things. Cam Martin from CH Storm Hills provides technical support to EPA Superfund Group. The 170 is actually the upper projection where it could go. That really wasn't what our most likely projection was for that, for the GN3 well.
Oh, good. Okay. Thanks.
Ken, that was the time frame for that, I think, wasn't it about 2013 that you were looking at?
When it was originally estimated, which I want to say was somewhere like 2007, it was about 3 years out.
Okay.
So that'd be about now, but we lost that well, if you remember, for about a year and a half or so because of the well cleaning problems that we have with that. So it's still in the future, but again, that's like the upper projection where it could go. That wasn't what it wasn't the most likely scenario.
Okay.
Okay.
Thanks.
Nicole, as far as you can tell, given the data you have in hand now, are the costs linear with the goal, your end level of hexavalent chrome that you're trying to achieve? That is, if you used 10 as your benchmark rather than 5, would the costs be approximately half at this point? There must be some fixed costs for which that wouldn't be germane, but I'm sort of curious about that.
Based on the curve that we're seeing so far, that does seem to be the case, that you just are getting a pretty good linear accumulation. There's not too many things that seem to be impacting, like sulfate and phosphate don't seem to really be impacting the resin much.
And with the clarification that except when you hit the threshold for the disposal, because
Yes.
there you just got an upper bound, and then you go into a different dimension for how you may want to dispose of it, and then the cost will be quite different.
I mean, it's always a speculation to decide where the state of California might go on a drinking water standard. I know from a federal perspective, we would be a long ways from lowering our MCL. But were we to do that, I think 20 might be an appropriate number. Well, okay, so then I start thinking all this through. This information, as you know, will be really, really important for our considerations were we to get to that stage down the line. And so if there's a break point there, that's going to favor one technology versus another, or one approach than another, those break points, that break point or any kind of break point would be really, really useful to know.
And we hope to do that, actually, when we're doing our cost analysis, which will start up pretty quickly now that we have some disposal information. So we plan on doing that, looking at potential MCLs and how that might impact costs.
So you on a televised one, you first heard it here. Bruce McLear offering maybe 20.
I'm merely speculating.
Can I ask for a point of clarification, or can you refresh my memory? What was the diameter of their pilot scale columns versus the columns that are out here? Are they the same?
No, those were 2.5 inches in diameter, the pilot columns. And these, I believe, are 8-foot diameter? Yeah. So the scale up seems to be pretty good, and not a lot of wall effects from the pilot A.
Same loading rate?
Yes. Yes, we kept the same conditions.
Thank you.
Sure.
Oh, one quick point of clarification. You said you were operating these to the point of breakthrough at 5 parts per billion on your lag column?
On the lag column, and then change out the lead at that point.
Change out the lead column, okay.
So we think we'll be at about 15 parts per billion coming out of the lead at that point in time, if we look back at the slide.
Okay, right.
So where you see the about 95,000 bed volumes.
Right,
Yeah.
okay, gotcha.
Which is
Thank you.
exactly what was on pilot.
Right.
Sort of circling back on, I know we went through an exercise talking about the selections of the resins and stuff. We didn't know about the formaldehyde issue at that point. Would you consider, well, we haven't looked at the costs completely yet, but one of the options I hope you're left open is sort of a reconsideration in view of the ultimate costs for the management of formaldehyde, and maybe look at some of the other resin options again.
We did test 6 resins in pilot testing, and 2 were effective. One is not yet NSF certified at this point. But that is a good question, and there are some other vendors that have been working on developing weak-based resins now that they saw that this was effective. So hopefully we'll have some competition
Great.
in the future.
You're absolutely right. And Nicole and I were just talking about that yesterday from a utility operations point of view. The formaldehyde's a real big pain. Mm-hmm. If you can't have certainty in being able to swap out your resin when you need to swap out your resin and minimize that time, it's a real problem. And that'll translate to some O&M cost, but at the very first level, it's not a reliable process if you can't control the formaldehyde.
Fair enough.
And the other resin did not have a formaldehyde base. It was an epoxy polyamine. There might be other issues associated with that. Certainly. So that would need to be tested.
Fair enough.
Yeah.
Thanks.
So on the slides that were titled your uranium mass balance, what sort of closure did you get on your mass balances? Are these all based on laboratory numbers?
They are, yes.
Okay.
We measure the uranium concentration in the water periodically in the influent and effluent, so we know how much is going on to the resin. And that's pretty important in terms of whether you need to get the specific license to be handling radioactive waste. And that is not the case here.
So when you actually did the uranium measurements on the resin itself, how did that close with respect to the calculated amount that was absorbed?
Yes, it actually did, yeah.
To what degree? Like 90%, 95%, 99%?
It's pretty close. Like if you look at the .054, which is expected, 0.054% expected for the normal operation, and then you look at the point we're at, which is about halfway for this resin bed, we are right now at .0259. So it's a little bit more than at the halfway point, which is about right where we're at.
You're pretty close.
Pretty close.
Yeah, good.
As good as you're going to get, I think, for different methods like that.
Right.
Yeah.
Thank you.
I have a question on that.
Sure.
Actually, I have a few I wanted to throw at you. Okay, on the uranium, though, your numbers you had up there, the 25% port sample was like 0.39, pretty high. The 50% port was at 0.075 or something like that. And then the composite, which is supposed to be 25% port, 50% port, and 75% port, came in at 0.025. So those numbers don't really jive. Because even if the last sample from 75% port was virgin, it still would be well above 0.025. So something doesn't seem to add up in those numbers. I agree with you, the overall numbers sound good, but
right.
that compositing sample somehow just doesn't seem to jive. Can you explain that?
And there's the question about where these resins are really being pulled from, which depths they're really pulling from, and whether you're having the bed moving around a little bit when you're pulling out resin samples periodically as well. We can go back to that slide. The uranium, the one with the red table. It's the other way, up. Yep, that one.
Yeah.
Yeah, because when we first saw these results, we were shocked at the level of 0.39 that we saw, and we said, oh my gosh, this is accumulating so much uranium. But it is possible that we just got the very surface layer or something like that.
But maybe the 25% port and 50% port are not representative of those depths.
Exactly. So I feel much more comfortable looking at a composite sample, or at least taking, we also this last time took samples at the 3 depths, and we'll make a composite number ourselves. Yeah, that's one of the inherent problems with the resin sampling, I think.
And then when the beds finally exchange, are we going to try to do a composite of the resin after it's removed in some way that's more rigorous?
Or at least a core, yeah. It would be ideal to be able to mix it up and then take a sample. That's the goal. I don't know how.
How about the plan? Is it the plan? Okay.
Yeah.
Okay, good. Okay, next, switching gears on you. When you guys met 3 or 4 years ago, the big issue for the WA system was ticks. The concern was when we reduce hex from the trivalent, something's being oxidized. What is that? Are we losing something from the resin that's going to be some kind of VOC into the water stream? And you didn't really have a slide on it, but you mentioned at one point that ticks were not showing up. So can you elaborate, like how many samples have been done on the effluent water? Is it the effluent water from the ion exchange beds, or is it blended from the whole plant? And so how many times have you looked for ticks in effluent water, and what have you found?
This is a question for Richard Charles, if you recall. I know it was done initially.
And by the way, we did have more than just formaldehyde.
Yeah.
We did have some nitrosamines, and there were a few other loose ends, minor stuff. Like ketone
But it all
was in
resolved
there.
pretty quickly?
Those resolved quickly.
So I believe we did, sampling every so many hours initially of flushing to make sure, we were getting nitrosamine flushed out and other things.
So I don't want to put you on the spot today, but maybe as some kind of follow-up, let's follow up on how many samples have been done for ticks and what actually has been found or not found, ideally. Because that was the key thing from this panel a few years ago.
Yep.
Okay. That's it. Thank you.
Okay, we'll put that on the list. Thanks. Okay.
Any other discussion questions on the weak-based iodine? Hearing none, we can proceed with the next part of the presentation.
Okay, thanks, Pat. We'll move on to reduction, coagulation, filtration. Next slide, please. Yep. Back up to the pictures, thanks. The idea behind this technology is that chromium-6 is reduced to chromium-3 with the addition of ferrous sulfate, which in the process is then oxidized from iron-2 to iron-3. And then the iron-3 forms particulates that chromium is then associated with, and those particulates are removed by filtration. So what this means in terms of what the process consists of are 3 reduction tanks in series, each contributing 15 minutes of detention time. And we did that on purpose. Instead of making one giant tank, we wanted 3 so that we could potentially reduce the amount of reduction time down as one of the different types of optimization schemes. Because in the end, one of the primary goals of the demonstration facility is to identify what pieces of the process might not be necessary, how can we really reduce the cost of a full-scale treatment facility, and the footprint as well. So we have the reduction tanks in series first, after the ferrous sulfate addition. That's followed up by an aeration tank that provides oxygen to the water and is intended to oxidize any remaining iron-2 that might be in solution. That's followed by a rapid mix tank for polymer addition to build up the size of the particles so that then they're more easily filtered through the dual media filters that consist of anthracite and sand. And then finally, there's a backwashed settling tank. So periodically, these vessels do need to be backwashed to remove the particles that have built up. And so then there's this tank that you can see right there in white. That's a cone-shaped tank that's used to settle the backwashed water, and then the water is decanted off and sent back into the treatment plant to minimize water losses. And then the sludge is sent to this sludge bin right here, which is a passive means of dewatering the residuals. So instead of having like a belt filter press, something more costly, the idea is to have the water basically go through a felt liner in this, what looks like a dumpster here, and the solids stay within that felt. So this facility was started on April 13th. Some of the startup and operational issues that we've had with this particular process, one of the primary things is that there's a lot of moving parts. So you'll see a lot of different types of issues. The first one was total coliform positives that we saw during startup. This was resolved a number of ways. I was just talking with Charles this morning a little bit more about this. One thing was sealing the open space. There was a little bit of open space at the top of the vessels and the mixers, around the mixers. So that was actually sealed. We thought that we actually saw some bugs getting into there, so that was a potential source of bacteriological contamination. The other issue is that there was a pipeline constructed to bring water to this facility, and that sat stagnant for a period of time and might have built up bacterial issues. So one other thing we're seeing is values of total coliforms recently increasing again, along with HPC values. And here are some of the results just from the most recent sampling when CDM did daily sampling to try to get at what was going on here. Now there's a lot of data on here, but just to show you, this is again HPCs, and here's the date on the x-axis. And the effluent concentrations of HPCs are the blue circles here, so you can focus on those. And so ordinarily they're fairly low. Then we did start to see some higher ones. We saw some lower ones, and we saw one that was way up here at greater than 5,700. Compare that with the influent. The influent values are always down here, not non-detect usually, but pretty low, in the single digits or double digits. Similarly, after ferrous sulfate addition, they're pretty low as well. We start to see some increasing in the reduction tank and the filter influent, which is after aeration and rapid mix. And then we see the highest values generally in the sludge mate effluent, so the water that's coming through the felt where the solids are, which can make sense, and the settled backwash water, those are the pink squares. So you do see some down here, but a lot of the sample results are up here. So as a result, the backwash water recycling that we were doing was stopped on August 19th to see if that could help bring things back under control. And since this data, we did start to see it coming back under control, and Charles indicated to me that things seem to really have been cleared up quite a bit since this data. So what this meant, though, was that you are getting a pretty significant loss of backwash water. We think it's about 4% of the flow of the process, although we'll have to do those calculations exactly down the road. But one thing that we wanted to do is try to really conserve as much water in the process as we could. So that's problematic if that's the case. And there's an issue with this particular technology that you can't add chlorine to the process because it will reoxidize the chromium that's reduced. So that's one limitation that has to be dealt with when we're doing this process. One other thing to note here is that there might have been another source of HPCs, which is we discovered in early August that the aerator was not aerating the water properly. So we weren't really getting bubbles. The diffuser holes were clogged, and I'm going to talk about that in more detail. But there's the potential that might have introduced some HPCs as well to the process. So luckily things are coming back down to normal, and the levels are getting low. But as Charles was mentioning, this has happened a few times. So this process does seem to be a little bit more, have a tendency to develop these kind of issues than the weak-base resin. Just showing one of the things that might have contributed to this problem and to seeding the process is the backwash water storage tank. We did see a significant buildup in the sludge and also some media, some anthracite in there. And so Rich of CDM actually had to go in there and clean that out by hand. So one thing in the future would be to consider putting in a mixer or something like that to allow, good mixing after, to break this up and then allow the water to settle. But this was something that happened. And since then, they've also modified the drain line to be a little bit bigger too, to handle more. Okay, next slide. Now some other startup and operational issues. The ferrous field results we found to be less than ideal. We did get lab confirmation that oxidation occurred during our dilution of the samples. So when we were trying to validate the ferrous content of the ferrous sulfate solution, we'd get great numbers, great agreement with what the 5% approximately of iron in the solution, the ferrous sulfate solution, but then the ferrous result would be way off. And what we found that to be is most likely due to oxidation that's occurring during dilution, or it's a problem with the method itself, just not being accurate. And so we actually purchased some standards of ferrous compound, made up the standards ourselves from a solid solution, and we still saw that same problem. So it's not very effective to keep measuring ferrous in the field, but measuring total is really has proven to be good. And we did confirm that the ferrous content of the ferrous sulfate was as expected. Okay. Another change or challenge has been the clogging of the ferrous sulfate injection quill at the injection site, and also the clogging of the aeration tank diffuser ring holes. So here's, I might have done that, sorry. Here's some pictures of the aeration diffuser ring, and ring I mean square, where you can actually see on the right-hand side the size of the holes, which when Rich pulled this out and discovered that it was clogged, he re-drilled the holes and made them much bigger, and then we had confirmation visually that the water's being oxygenated. But up until that point, the aeration tank was sealed. So there's a significant period of time of this testing in which we don't know if the aeration was actually working. If you put your hand to the side of the aeration tank, it felt like it was, but when Rich opened it up, there were no bubbles. So,
And Nicole?
Yeah.
Where's the hole on the right side? Is it over by the...
Yeah, it's right by the number one. Right there.
That little teensy hole. Okay.
Hole.
Okay.
Yeah. So now he drilled them out to be double that. And now we're thinking it clogged again after 3 weeks of operation. And it's being used too. So one of the initial issues was the aeration wasn't on for 2 weeks, which is why we think it clogged up at that point, because there was a significant period of time it was operating and the iron hydroxides could build up in there. Okay. Next slide. Thanks. Do we want to go through again some of the operational issues before moving forward to the results?
I'm okay.
Let's break and discuss that if you have any questions. Done?
Not me.
Maybe there'll be more when it's tied in with the results.
Some things may not matter, Nicole.
Yes. Okay. So chromium removal, now here is the chromium concentration on the influent, which has been increasing from about 65, now it's a little bit over 80, 85, it's about 85 right now. And here are some examples of what happened at different points in time. So we did start the aeration on May 6th, but as I mentioned, the diffuser holes might have been clogged at that point. Up until this point, this was run at a 25-to-1 iron to chromium ratio, which was found to be effective in pilot testing, and a 24-hour run length. Now, two things were changed here. It was changed to a 30-to-1 and a 48-hour run time on July 13th. The iron to chromium ratio was increased because we were not really getting down to the levels that we'd hoped. We were getting mostly below 5 parts per billion, but in pilot testing we saw below 1 part per billion very consistently. And so we knew it could be done, and we wanted to figure out how to get to that point. So these two changes were made, and the concentrations did decrease quite a bit, at least in the next couple points. We did increase it one more time to 35-to-1, just to make sure. And then the diffuser ring holes were cleared out on August 11th, and then after that we got our first 2 less than 1 part per billion results. Okay, go to the next slide. Here's a blow up. So now we're looking at a scale of 0 to 8 parts per billion. So looking at what was in the noise there. So you're seeing here's our target of 5 parts per billion. So most concentrations were below 5. But we did think that some of these issues had to do with turbidity breakthrough. And right now we're actually working to take down a lot of information from the SCADA system and figure out turbidity trends so we can map whether this was the result of turbidity breakthrough or not. But it seemed to us that the turbidity was higher during these particular events, and that the particles just were going through and were not being built up sufficiently. So as a result of bringing the aeration back online, all of a sudden we got these much better values. And an interesting note that we've seen is that a 48-hour runtime seems to be better than a 24-hour runtime. Perhaps because there's a buildup of those particles, and then other particles that are smaller can flocculate with those. So that's what we're seeing right now. So what we've done at this point, we ran for 3 weeks at this 35-to-1 ratio and a 48-hour runtime. and we got these good results. So now we're dropping that back down to 25 to 1 and running there for 3 weeks and seeing if that's effective. Making sure that the aerators are run, that the aeration is effective, and then we'll compare that with some of the other data. Okay. So now in gray here, I'm showing a matrix of the different runs. So what we've done so far, breaking this up into 8 different runs. So the first one was no aeration, which was inadvertent, but we did that for a couple weeks, 3 weeks at least. And then the next run would be maybe there was an aeration step. We don't know for sure, and a 25 to 1 and a 24-hour run length. That was increased, as I mentioned, to 30 to 1, then 35 to 1, and then after the aeration brought online for sure, we have that run. So now that's the point we're at. We're running this one at 25 to 1. Now some of the other things that we want to test are turning the aeration off on purpose and seeing how that performs, this 25 to 1, and seeing if that does agree with some of these previous runs, if we don't get quite back down to 1 part per billion again. So verifying the effect of no aeration. And then if that, going back to adding the aeration again, if run 5 was effective at the 25 to 1 ratio, looking at less reduction time. So could we go from 45 minutes down to 30 minutes? If that's effective, can we go down to 15 minutes of reduction time? And in pilot testing, we saw that we could, as long as we had aeration on for those particular scenarios. Okay, next slide. So now the next question, and something that I posed to the PAC, is where else do we want to go with the study? You know, we think we really need to validate some of the initial findings. There was a significant amount of startup time and trying to iron out all of the different variables associated with this system. So we don't have very solid results at this point in order to say that the process can be optimized in these particular ways. That is.
Oh, it's my paper, sorry.
So we don't know at this point in time how we would change the process if we were to optimize it. So we wanted to use the next 6 months of testing in order to really get at how can we optimize this process, because we know that the costs are very significant at this full process of 45 minutes of reduction time, having an aeration tank, and having the dual media filters. So that's one of the biggest questions is how can we really get this honed down so that the costs are minimal, moving to full scale. So some of the other things that we could test, as I mentioned, verifying whether you need that aeration step, testing less aeration time. We could check 24 hours at the 25 to 1 ratio, make sure it's not the 48-hour, maybe it's a 48-hour runtime that makes the process more effective, which we should be able to get better results when we can download the turbidity data and evaluate that closely, be able to evaluate that question. We can also look at things like lower influent concentrations. We could do a blend, which might help to inform other utilities that are dealing with lower concentrations of how effective this process would be. And then also look at more optimized runs. So a combination of reduction time with or without aeration, lower influent concentration. So there's a lot of different permutations we could do. And so that's a question for the PAC. What else do we want to see? What do you think will make it, will be the most informative in the limited amount of time we have left for this study? So now the Aqua study, where we're at right now, we've evaluated the disposal options for the weak-base resin. We're assessing the residuals, characteristics, and the volumes for the RCF process. We had our first disposal of residuals, which are considered non-RCRA hazardous waste, if everybody remembers that flow chart. They are not radioactive, luckily, but they are hazardous from a TTLC perspective on the California wet test. So they were disposed in Buttonwillow at this facility in California. But we'll look at the residuals characteristics, the volumes associated with that, see if that matched what we initially had costed out. We're going to test other water qualities to estimate residuals volumes for other water qualities. We're looking at 3 different utilities around the state to kind of get some bookends there. And then also extrapolating the California utility costs for various MCLs, as I mentioned previously. And that's all I have for slides. Anybody has comments on the RCF process, we could get into a bit of a discussion.
Sure. Can I ask clarification?
Sure.
You did total coliforms from the RCF demonstration.
Yes.
Can you give us any idea what the range of values were? Did they kind of follow the HPCs?
They did follow the HPCs. Some were fairly high. Most, I'd say there were some where the HPCs were reasonable and their total coliforms were negative, or not absent. But there were some that were pretty high, greater than 23 even. So it definitely varied. It did seem to mirror, though, what was going on with HPCs.
What method are you using for that?
What method is that? Do you know? Color.
Is this water being blended also in going to the Glendale facility?
It is, although it's not right now, since having these problems. We wanted to get to the bottom of it before we're doing that. But it does. It's 100 GPM. Don't think I mentioned that earlier.
Sorry.
But it is being blended with the other water.
Thank you.
Okay, I have a couple questions. Your filter is a dual media or tri-media?
It's dual media.
Do you think to test the tri-media since you have particular, leach out the dual media?
That's a possibility, as is the potential for microfiltration. And that really depends on, again, where the MCL winds up. If we're at 20, we know that this process really is effective for getting below that level for sure in every case, even without being optimized. But if we really want to get to 1, that's another matter. And at this point, we're not comfortable saying that we can reliably get to 1 every time. And we are, again, looking at very low concentrations to know where we are with respect to the pHG. So there are a few, I think filtration modification could be needed if we wanted to get to a lower level.
And another thing is you determine the runtime. It's based on the Chrome 6. It's not based on the something like turbidity or other stuff, right?
Well, we'd like to base it on turbidity. We haven't gotten to that point yet, dealing with some of these other issues.
Okay.
But that is one hope from this process, is to get to that point where we can look at the turbidity profiles throughout a run and say, maybe we can do 72 hours. We don't know how long we can actually get, keeping in mind that there are some potential bacterial issues associated with that too. But in pilot testing, we tested 24 and 48 and found both effective.
So could you tell me more about your backwash procedure? Because you made a statement about 24 hours and 48 hours. It seemed to you 48 hours doing better job in terms of remove Chrome 6, right? So what's your backwash procedure? What's your target for backwash? You say that's good or that's bad?
How much do we need?
How much do you need?
I don't know that that's actually been evaluated yet. It's been just a procedure that Lane Christensen provided when they set up the facility. And we've been going back and forth a little bit because we don't think the air scour is not occurring, we just came to find out, not occurring during the backwashing. It's occurring when the water is stagnant in the vessel. So when we weren't getting down to 1 parts per billion, we really started to go back and look at a lot of these issues and try to figure out how we could improve filtration. And that was one thing we looked at. Well, maybe the air scour could be better. We do seem to be losing some media, though, out of the vessel and into the backwash settling tank. So there's some questions about how much expansion we can get, how long we want to run it. But yeah, that's one variable that hasn't been worked out yet. It might be worthwhile. Yeah.
I think some come from drinking water side about conventional treatment process. You all know those filter backwash have a ripening period of time once you put in service. Have you practiced backwash to waste? Otherwise, if you put these in service, you will have a ripening period of time. You will have some particulate. You will have high Chrome 6.
You guys backwash to waste? I don't know if when you first bring it back online, or does it just get served? We don't. I don't know that we've looked at that.
But that's
there.
We'll encounter.
A good question, yeah. I think we should look at that.
And when you take the sample to analyze, have you done any speciation about the iron? Is it how much in the ferrous, how much in the ferric? The reason I ask that question because you are talking about effect with and without aeration. The aeration basically is to try to convert ferrous to ferric.
Right.
But if you want to look into the impact with and without aeration, I suggest you to do a speciation about ferrous and ferric.
Right.
Yeah.
And we're trying to do that with the field kits, but finding difficulty with that. So it might be something that we have to do at the laboratory. We did do that in piloting and found that most of the iron was already oxidized by the time it was getting out of the reduction tanks. Because the level of oxygen in the water is pretty high. It's usually like between 5 and 8 milligrams per liter.
I know.
So there's a fair amount, especially at these low iron doses, when you're only adding 2.5 milligrams per liter. You've got plenty of oxygen to
But again,
stoichiometrically.
the purpose for you to do demonstration scale is deal with all the scale-up issue.
Right.
This is one of scale-up issue.
Yeah.
We needed to take sample to do speciation.
Yep.
Okay.
Steph? Wait for Nicole to finish writing her notes. Two quick questions. The first one, and perhaps for the second one, I'd appreciate any state or regulatory, opinion on that. When the water from the treatment, you said it gets blended, the effluent gets blended. When is it chlorinated?
It's chlorinated after the GAC process in the Glendale water treatment plant.
So
It goes through the facility for the VOC treatment.
okay. So the question I have is, did you discuss with the regulatory framework on their opinion on whether it was necessary to try to reduce the microbial population in the first part of the process or depend on the ultimate disinfection, and if there was some tolerance level available? I'm looking at Jeff, but
Yeah, I was going to look at Jeff too. I know that there's a limit in the permit of 500 for HPCs.
Well, our concern was
Jeff, could I ask you to come to the microphone? Thank you.
I'm Jeff O'Keefe with CDPH and the district office here in Glendale. Our concern primarily was contaminating the carbon media and causing operational problems at the operable unit treatment facility. So I think we had discussed the possibility of chlorinating the effluent of the RCF, which would likely all be off-gas during the airstripping process, which is the first stage of the treatment. And I know it was discussed, but I don't recall any decisions being made on that matter. But I know we considered it. I don't think there was chlorination facilities included as part of the RCF treatment. And I don't know if there was a way to add it at the other facility, but it's something worth considering. We just thought that this would be a short-term problem. Unfortunately, it's had some duration. Okay.
Thank you, Jeff. Just options to consider. Thanks.
One more things I would like to ask. Is that hole you drill, is that the metal pipe?
It's PVC, isn't it? Yeah, PVC.
Or even PVC is clogged? We never experienced that. We use a ferric chloride. And now one of treatment plant, we use PVC. Maybe a hole is very big anyhow. We never experienced the clogging of the hole.
I'm not sure if you do it at your plant, but there's another one I'm involved with that a lot of you know I'm involved with, but I can't mention it because it's a confidentiality thing. But it treats 4,000 to 5,000 ppm of hex chrome down to 1 using the same process as here, except that we do use a microfilter instead of a media filter. In that case, though, we recirculate sludge, and that sludge provides a lot of surface area for precipitation, so it helps keep the precipitation off of the equipment. It's a huge difference. There's the iron's first added in a part of that plant where it doesn't have recirculated sludge, and then it flows into the second tank where it does. The pH probes in the first section will scale up weekly, and we'll have quarter-inch thick scale in the tanks after a year. But downstream of that, where we've introduced the sludge and providing that extra surface area for precipitation, the probes stay clean for weeks at a time. The sludge don't scale. We have eighth-inch diameter holes. Aeration systems have never had to be drilled out, to my knowledge. So it's a huge impact. That may not be practical here because in that system they have a clarifier, so it's a nice way to pull the sludge out and bring it back to the front. Here, if you go right to a filtration, it would simply add to your filtration load. So it's kind of a dicier subject. And then since while I'm up here on the filter, I definitely support looking at a microfilter. That's what we use at the other facility. And there's a really easy test we could do here to check to see how that might make a difference in your performance. And that might be to take some of your current media filter effluent, your plant effluent, and have these nice little microfilter syringes. Mm-hmm. And you have different ones, like a 0.1 micron, 0.2, 0.4, and do samples with those, and that will give you some idea how much additional removal you might get of precipitant, and therefore lower, hopefully, chrome, with just doing a lab test, if you will. So it's pretty easy.
I think that would be worthwhile, yeah.
I do.
And one other thing about the diffuser ring is that in the piloting we used more of a coarse bubble diffuser plate. So that's also something that might be more effective. That wasn't chosen here by Lane, but
I think his point is well taken because based on my knowledge with the TOPOC, the use the same process, they use a microfiltration. They don't have any of those issues.
So, Nicole, just as far as the costs go, when do you expect to have some sense of the RCF?
we're hoping in the next couple months because we now at least have the first disposal of the residuals there, and it'll still be tailored a little bit because we are going to do some of these additional tests and see where we can get from a capital perspective. But at least from the O&M perspective, we can kind of bolster those estimates we had already.
For the residual study?
We actually have started those cost analyses. That's a little easier. It just, especially since we're getting pretty good bed life consistent with what we're expecting. So that can be done concurrently as well. Yeah.
George, I'm sorry.
Go ahead.
I was going to ask George to go back to the slide with the RCF demonstration study. It's 2 slides back. And, I'm sorry. You've gone past it. It's right near the end. It's back, yes. The other direction. Sorry, George. Right there. I think when you presented this slide, Nicole, you were asking for more feedback about the methodologies here. I didn't hear any, and maybe we should discuss that.
Yep, and what we should prioritize. Because I don't think we're going to be able to do everything we'd hoped initially because we did have some of these initial startup issues and had to work through them. It's a question of what we think is the most effective use of our time.
Do you have a feel for what the critical variable might be for scaling the RCF process?
In terms of cost, the reduction time, the reduction time being 15 minutes times 3 is pretty significant footprint and dealing with the sludge and so forth that builds up in those basins. So that's one critical variable in my opinion. The question of aeration is another one because with the VOC contamination of this groundwater, you do have to have aeration treatment, air treatment. So that becomes a cost factor as well. Those two, I think, are the most critical. Another thing that we've also been working through is what to do with the backwash water, how to kind of optimize that process a little bit more, because we have seen some of these problems of buildup of the solids in the cone, and whether we want to recycle that and figure out a way to try to minimize solids buildup. So those three, I think, are the most critical. But I'd like to hear other opinions on what you think.
Well, if you're talking about reduction time, don't you think you should go back to the basic, look into the contact surface, those array? It's not just say you use a current configuration to reduce that. That's probably easy way, but might not give you an answer. Look into different kind of reactors if you talk about the reduction time. Mm-hmm. Because your system do have some deficiency or some kind of scale-up issue. So that's, if you want to look into the reduction time, that might be some good way to look into that. Rather
whether
than
you
just
have like
reduce.
serpentine piping or something.
Something like that can increase those contact.
So are you talking about like the initial mixing?
I'm talking about different kind of reactor probably, or you want to have more flow patterns more efficient to react with the chemical.
So like where the initial injection of the ferrous sulfate
That's
is.
part of that, and how the flow, those
So you have
mixing, those
baffles
kind of things, those kind of
Right.
things, yeah.
I don't know how much of that we could test in this particular demonstration study. I think there's definitely value in considering all of those issues.
But that's a cost.
But yeah, the capital expenditures there might be
Yeah, that's right.
too great.
Nico, will you be able to study out the microfiltration part? And I know Ken's is a great idea in terms of using the syringe, but I was hoping perhaps even a little more substantial.
Again, I don't know that the budget's a little tight at this point. I think we can do the syringe filters. Certainly, that would be a good approach to at least get an idea.
On that. It's just a sentiment that if it's working somewhere else already, that gives me more hope for its application as opposed to something that's being just piloted and so forth. So it's an existing technology. It seems to be very promising and working.
It's also more effective biobarrier too.
Mm-hmm. Yeah. I mean, I would speculate that is a pretty known variable. Like, we know pretty for sure that microfiltration will work.
Right.
Based on what we've seen in other places and iron removal systems. Optimization, on the other hand, would need to be done. So it's a question of whether to go in that direction down the road is to test that out.
Yeah.
Yeah.
You know best. You're juggling a lot of different things with the study. But my 2 cents worth would be that not to overly indulge in trying to force this technology to reach an endpoint that is known to be reached with the microfiltration. So save some time in that way and perhaps focus on some other aspects. If you're going to take the issue and the syringe thing and consider that as a known technology, then don't bother working on pushing this one that far.
I'd concur on that one too, and I would ask whether there's been a sufficient publication of the approach that you're working on, so that that's in the record, that we can reference it and consider it here. Because really, if that's a superior approach, and it has at least a good chance that it will work here as well as it's working in your circumstance, I'd agree with Pankaj that better that you take a look at the other components of O&M that are more problematical, and maybe think that this will be where you go for the long term.
So are you guys thinking to do maybe just the first couple points, and then in an ideal world you test out microfiltration or something else like that as well? Or would you not even do those first?
I guess the question is, how certain are we that the microfiltration approach would actually be a better approach than using the media filter that you're doing now. And I just think if you're actually utilizing it in similar circumstances, using a similar sort of approach, well, what do you know?
And there's a cost issue associated with microfiltration being more
Of course.
costly and
that.
having more loss of water. So you often need to do pilot testing of microfiltration in order to minimize your water losses, trying to do
Right.
some.
I'll answer what I can. Again, I'm on a confidential agreement, and that client is not published papers. But I do know Dr. Liang has access to all the regulatory required documents from that project, so I don't know if that can be disseminated to the PAC or not. I suspect it probably can. It's probably public record out there through those means, but not like published papers per se. Okay.
It's public information, though, right?
Right. One more thing on the microfilter, not that I'm really pushing that, but I do think it's a good option to look at, is also there's a good chance you would not have to do polymer addition with that if you go direct filtration. And that would be helpful for these guys in a number of ways, too. So,
Well, I think that facility, the unnamed facility,
no, it does.
use
It does.
polymer.
It does.
Yeah.
But that's because of the clarifier step.
Yeah.
And we were doing very trace levels of iron addition like you do here, a few ppm.
Yeah.
You wouldn't have to do. You don't have to do the polymer for the microfilter. You do it for the clarifier. So if we only had the trace levels where we're just going to let it all go to the microfilter, then I think you can go with that polymer, and that would be another potential advantage.
Yeah, that's actually, and that leads to another good point, which is, that you probably would want to pilot test if you do a direct microfiltration process and not have a clarifier upstream.
Yeah, and I don't know if it's possible for this test, if you can get a little rental unit, a 1 or 2 GPM, hook it in on the effluent aeration tank maybe. That'd be nice. I'm not sure if that's practical or not, but that's something for you guys to consider.
Thanks.
Sorry, I'll adjust the panel a little. When you know operational problems with those?
Oh, yeah. I mean, every plant has
Before you
issues.
answer, the public can't hear the comments that you're making from the floor. So, Jeff, if I could ask you to just come to the podium.
Sure. It's Jeff O'Keefe with CDPH. I was just, while we're on the topic of microfiltration or membrane filtration, I was just curious if there are any known operational problems with the membranes at the facility that Ken Martins is familiar with, such as fouling of the membranes.
Yes, exactly that. but most of the problems with fouling have been because of the polymer. And in your case, if you do direct filtration with no clarifier because you're doing trace levels, then that problem may not exist in an adaptation to this plant. But that has been definitely our issue. We can clean the membranes, but the cleaning effort is significant labor, so that has to be accounted for if we were going to try to account for that. But again, I think you might be able to avoid the biggest problem we had there by the way it would be adapted here. Okay?
You know, my understanding sometimes is assisted by thinking back to the origin. And maybe I zigged when everybody else zagged, but why did we go with media filter instead of microfiltration in the first place?
Initially, I recall initially it was a lower cost, and when we tested it in the piloting, we found it to be effective. So, and I think we're getting there. I think we've gotten to that point where now we're seeing those kind of performance levels of less than 1 part per billion. But the first 5 months of operation didn't get us there. I mean, it still got us to mostly below 5 parts per billion. But yeah, these are other considerations if we want to make sure we're down at these lower levels. It's a possibility.
I'd like to clarify something, Peter, and I don't want to put Nicole in a difficult position. We totally understand this study is to do due diligence to the technologies that have been chosen, and you got to get the most you can. There's a wealth of knowledge out here that will be useful in other aspects for this media. And so perhaps I should couch what I had requested, and Bruce too, is more for the consideration of the study sponsors to add a dimension to this rather than, we are not telling Nicole, stop completely exhausting what you need to do here, but we are also seeing a practical side to what has just been shared at the meeting for your consideration.
I think going down the road of the media filter is where we're at, and I'm not actually suggesting we don't unless it was absolutely clear that that approach was superior and that down the line people would be almost forced to move away from the media filtration work, and then if you're going to spend a limited amount of remaining resources, work on the other components that you really have to nail down. But I'm not actually hearing that that's the case at this point. The media filter still could be a plausible approach if you can get it optimized. Yeah, that was the only reason I went that direction.
Good.
Well, we're coming to that time in the program to wrap up. I thought I'd take this opportunity to thank the panel members for participating on the behalf of the City of Glendale and the sponsors. Before we do that wrap-up, perhaps we can poll each of the panelists to see if they have any wrap-up comments that they'd like to make. Pankaj?
Okay. Thank you. I feel very privileged to be part of this pack. We have learned a lot along the way. I think there have been surprisingly good pieces of information that have emerged from this exercise. You've got an excellent team of folks working on this and the products you're using. It has taken a while, as we knew it would, and there's always emerging technologies that will always compete for our attention as we embark on something like this. And I'm just hopeful that given the uncertainty of where the California regulatory endpoint will be on this, that you will emphasize to whoever you need to, that to keep the door open before a final selection of more conclusive work is done on some of these, because as Bruce also mentioned, it is going to be very, very critical on where California sets its level, because some of the costs, some of the processes that we have looked at could significantly be altered depending on that endpoint, and it will have a big impact on costs. So with that, good luck with this. It's going well. Thank you.
Thank you. First, I want to make my point very clear. I'm not a politician, so I cannot say the very good words. I'm more practical, focus on techniques. So my point of view is this. You already went through the bench, pilot to demo. Obviously, next step is you want to implement the full scale. You should put more focus on all the issues in terms of your future full-scale design as well as the operation. I want to say you are doing a wonderful job, produce a lot of information, but from my point of view, you're still short of quite understand if you're going to have a full-scale design as well as how you're going to operate that. And because a lot of practical issues you need to deal with in order to serve this water. One thing I should apologize, I'm not too sure your water going to serve through this process direct to the public or going to have downstream treatment to blend that. That will be different. If you have more downstream treatment, deal with VOC, GAC, that's one story. If you're going to serve this water direct to the public, you have a lot of issues you need to deal with that. So again, thank you. Be honored for me to participate in this. Thank you.
Thank you, son. Bruce?
This is probably of the projects that I've been project officer for in terms of EPA grants, the 3 grants, I've certainly been most pleased with the quality of the work that's come out of this, and I've said this many times, and publicly it's just a good example of taking a problem from the beginning and just continuing to move it along very thoughtfully with a lot of disclosure, with publication, stuff getting out into the print, not being held back, getting out there for others to use. And this will be, as far as I can see right now, the data set that would have to be used by the state and almost certainly will be used by EPA. So it has to be done well, and I'm glad to see that it's going well. I have to concur with Sun on this one, that the practical aspects of the next level of scaling have to be front and center, to the point that not a question for you so much, but a question for the city is what would be the opportunity or the thinking in terms of trying to acquire some additional funds to make sure that this is done right at this next step up, that we don't get it just there and be out of funds and then be forced to just go someplace with it. Maybe there's other stuff that we can, other information that we can eventually bring into the discussion, but it would suggest that I know that these grants are almost exhausted from the federal side. I don't know how much R&D you can use with the state funds, but it might actually suggest getting one last round of federal funds to make sure that this is done right at this next level. Now, the brain power here can say whether that's a good idea or not, but I'm hearing that it's the right direction and would like to mention that.
Thank you, Bruce. Peter Kavunis, Assistant General Manager for Water, has joined us as promised during the meeting, and that sounded like a question for Peter.
Yeah, that's what I was looking at.
So perhaps let Peter take an opportunity to respond.
Thank you, Pat. Actually, I'd prefer if we let Rick have his comments, and then maybe I can provide some comments for the City of Glendale addressing Bruce's comment as well.
Oh, thank you, Peter. Going last is always tough because I think all the major points that have been covered by the previous panel members. But again, I too would like to thank the city for allowing me to participate in this project from the very beginning. It's been a very interesting project, and I think a very, very purposeful one in the way it moved forward, studying the problem, going from pilot to bench scale to pilot to demonstration project. And I think my only cautionary note, and I agree with you, Son, with respect to the next step taken, but I think I also, being a former regulator, like to maybe ask that we think about these not just from the standpoint of being demonstration projects, but in some cases, these technologies will be able to stand on their own or be inserted into other treatment process trains. So from the standpoint of the state of California defining a best available treatment technology, I would like to see some of this information move forward and be used by the state to identify best available treatment technology. Because I know there's always that, what is a full scale? And, the state has to have a full scale treatment process before they can identify it as a BAT. But in my mind, some of the sizes of these demonstration projects are actually the same sizes of many of the small systems and can be applied in those systems and should be considered, I think, as best available treatment technology. So we shouldn't let the verbiage and just the language of the law necessarily dictate our actions going forward.
Good point.
So, thank you again, Peter, and thank you, Nicole, for a very good presentation.
Thanks.
Thank you, Richard. I don't want to neglect Heather Collins, who's on the line, theoretically. Heather, if you're there, would you like to comment at this time?
Sure. I don't have that much more to add, but just like to thank everybody, too, for our participation. I think the work that the city has undertaken in the past several years is very, very much valuable in the time when we finally get a public health bill from OEHA and move forward in our regulatory process of adoption in identifying and looking at the costs and operational issues that surround such treatment and the development of a BAT, all of what you're doing is extremely valuable. It'll be interesting in the cost analysis because of Glendale's power rates versus others in the state. That will definitely be interesting. And as more and more manufacturers come with available resins or resins that they want you to look at, how that all folds into an operational issue, whether you stay with that sole source resin that you've gone through all your different testing with versus an adaptive type of thing. If another utility were to take your designs and take the treatment and utilize another resin, how that all kind of plays out in the future. As Pankaj and others have mentioned, we definitely don't know where that public health goal is, when it will come around for DPH to have the ball in our court to move our regulatory process forward. So it's a waiting game right now, and I understand it's a very difficult one for the city to be in to continue to move things forward as far as a goal and a level to strive for ultimately. So I think everybody's doing great work, and I appreciate the opportunity and information that comes to the panel and the PAC on a more frequent basis. I think that's great, the way that you're keeping all of us updated and integrated into your work that you're doing. So thank you.
Thank you, Heather. Perhaps, Peter, this would be a time for you to respond.
On behalf of the city, of course, I can't tell you enough of how grateful we are to have such a great team working on this project, and really thanking both individuals and the organizations for providing the individuals to us. LA Department of Water and Power, Metropolitan Water District, EPA, East Bay Mud, and Department of Public Health, and not just in your time, but also the time of the folks that support you and the time of the folks that are here in the audience. In addition to Heather, we have Jeff and staff. We have Aqua to thank. We have the GRG to thank that's stepped up as well. Ultimately, a project like this hinges on money. It's all about money. Because of the great support that we've gotten, and if I forgot anyone, I apologize. It's impossible to remember everyone, but because of the great support, we've been able to make the commitment to put up the city's money first and then wait for reimbursement next. On a perhaps a slightly bitter note, we are still waiting for reimbursement for state grants that we've been promised. And so the concept of asking for more is one that we're open to, but we're approaching it cautiously. The city is in a financial difficult time. We have had reduced revenues. We have had increased expenses in our general operation of the utility. So the concept of us putting more money up front is one that we have to approach cautiously. But I think, to a person in Glendale, we believe in the value of the work that we do here on this particular project. Truly believe it, and we believe that it adds value to the entire state. And I think that will bear out when the day is done. And so we'll keep fighting for it. And having your support and your presence here really makes it possible. As a last thought and comment, I would like to personally thank Don Froelich and Leighton Fong for helping and organizing this day today, as they have really been the backbone of the project. I think it's obvious to everyone the love and attention that they've put into this project and making it possible for all of the work to happen as well as our meeting to happen today. So thank you, and a job well done. Pat, I'll turn it back to you.
Thank you, Peter. Thanks to the panel and to Nicole and members of the consulting community, those that support us, and from the regulatory side. Appreciate your help. I can't say enough how much this project means to the city of Glendale. Peter said it much better than I. In conclusion, then, we'll wrap up today's PAC meeting, and we're going to adjourn for lunch. Thank you very much.